Hi everyone, today I'm going to present our work, Benchmarking Language Model Creativity, a case study on code generation. My name is Yining and this is a joint work with Dixuan Wang, Tianzhen Li, Dongwei Jiang, Sanjeev Kanduper, Men Jiang, and Daniel Kshabi. Before talking about machine creativity, let's think about what is human creativity and how we define human creativity. And from cognitive science and psychology fields, like researchers from these two fields, they made a common agreement that human creativity can be understood or can be analyzed through two kinds of thinkings, divergent thinking and convergent thinking. In divergent thinking, they test humans' adaptability to explore new environments or constraints given a limited number of resources. For example, how can we make coffee without coffee filter? And divergent thinking can be further viewed through the lens of P creativity and H creativity. Here, P stands for psychological, and we say a valuable idea is P creative if the person in whose mind it arises could not have come up with it before. For example, if I come up with an idea or solution for how to making coffee without coffee filter for the first time, for me, then the idea is P creative. And for H creativity, H stands for historical, and we say a valuable idea is H creative if it is P creative first, and no one else in human history has ever had it before. And once my idea, my solution for how to make a coffee without coffee filter, the idea has never happened or be think of during the entire human history, then we say that idea is H creative. And before 1990s, people think, oh, human creativity is only about novelty. It's only about divergent thinking. And now, after 1990s, people may, researchers think more about convergent thinking. It tests users or humans' purposefulness to achieve a given goal, like the accuracy, the correctness for solving a problem, or the coherence or logic of a generated story. By considering both convergent and divergent thinking, nowadays people can say, "Oh, idea is valid. Idea is creative, because it is novel first. It has novelty first, then it is valid." Now let's introduce how we evaluate creativity and what's the protocols for evaluating creativity. And from these old psychological works, they said human creativity is viewed as taking place in the interaction with a person, environment, or another model. And similarly, the essence of machine creativity or the language model creativity should also be captured from its interaction with the environment, like with the current state, and also with the interaction with past human knowledge background. And this understanding reveals that our creativity evaluation, our machine creativity evaluation should be dynamic, and because an individual's creativity vary under different contexts, right? So there are two protocols we proposed that our evaluation has to follow. First of all, it needs to be state-aware. The evaluation should be adaptive to different contexts, and also human-grounded. We need to compare our results, comparing our solutions to those historical human solutions. Now let's introduce how we evaluate machine creativity in this work. And before that, we have to clarify that we define and evaluate language model creativity under constrained problem-solving settings. And we admit that for different, there are other ways for evaluating language model creativity from different tasks, like using open domain question answering tasks or from those story generation tasks. And we agree, based on our problem-solving settings, we argued that an effective creativity evaluation method should be based on the spectrum of maximal creative solutions obtained from large language models. And based on these arguments, we found there are two limitations for us to evaluate language model creativity. First of all, eliciting creative solutions from language model is difficult because it tends to repeat what they have seen during the pre-training. And also, we need a unified metric that can quantify both convergent and divergent thinking, which we argue that it is important to consider both the convergent and divergent thinking. To quantify the first limitation, we propose denial prompting. It is a simple but effective prompting method that can encourage language model to think creatively. Here is how it works. we are given a challenging problem, and so there is a universe of all possible solutions for that problem, and also we gathering historical human solution from it, and it is denoted, you can see in the purple circle. And then we ask language model to come up with a solution without giving any constraints or hints. And we expect that like the solution, language model solution set space is highly overlap with those historical human solutions, because that's where its pre-training data comes from. And then we ask language model, please don't use one single technique that they have used in this solution space. And there will be a new language model solution space that is less overlapping with the previous human solution space, like in yellow, and the historical human solution space. If we keep doing this denying process, we expect one day maybe language model will think out of the box, think to come up with a new solution that no one in the human history has come up with before, and we consider that solution to be truly creative. So that's how denial prompting works, and we hope it can push its language model to think out of the box and to elicit creative generations to its fullest extent. And based on these denial prompting methods, we now can construct our dataset for benchmarking language model creativity. We call it a NEOCODER dataset. We first compiled 199 latest Codeforce problems. Codeforce problems are very challenging coding problems even for humans. And we extract 30 correct human solutions online, like for per problem. And we also retrieve all test examples to test whether the generated solution is correct or not. And we feed the retrieved problems to denial prompting pipeline with 5 maximum iterations to obtain our final dataset, NEOCODER. And this chart shows the statistics of our dataset. You can see like for the number of instances, number of problems, it is monotonically decreasing over like number of constraints. This is because denial prompting like potentially reaching a point where it can no longer generate new constraints after a certain number of iterations. And now we present the distribution of techniques in our dataset. And there are 2 takeaways. First of all, you can see the x-axis here is the number of constraints or the states. The y is a proportion of the top 5 techniques. And with less constraints, models tend to use easy techniques like for loop and if statement. But with more constraints, added, these common techniques are used less. And if we compare it with human distribution, like human technique distribution, you can see in the absence of any constraints, the model default to those common and access techniques. This behavior is just like humans. The distribution of the first and last column are quite similar. And this observation echoes our early claim that eliciting creative solution is very crucial for creativity evaluation. And based on our dataset, we now can compute our creativity score, which we call as NEOGAUGE. And how it works is we have a problem from our dataset, we feed the problem to language model, and it will give us an initial solution without any constraint. And then we detect what kind of techniques used in this generated code. And also we calculate the following 3 matrices: correctness, whether the code is executable, is runnable, and also passed all test examples, and whether the constraint following ratio, whether it follows the given constraints. And the false state there, because there is just no constraints, so it is constraint following. And we also compute edge creativity, which basically is the proportion of techniques that has not used or has not been seen in the collected historical human solutions. So that's the 3 matrices we need to compute for each state for NEOGAUGE 0. And we keep doing this, keep adding more constraints from our dataset. Like for state 1, we just don't use for loop, and the model will generate new solutions, and we detect what kind of techniques used in this solution, and we compute the same 3 matrices, and keep doing this. So in this example, we have 3 NEOGAUGE score, NEOGAUGE at 0, at NEOGAUGE at 1, and NEOGAUGE at 2. Adding these 3 scores together, we can compute our final NEOGAUGE metric, and we compute our NEOGAUGE as the probability of language model generating correct solutions that meet the given constraints. So that's convergent thinking, and also exhibit edge creativity. And edge creativity here symbolizes divergent thinking because it quantifies how much new techniques or solutions that human has never come up with before. So that's how we compute our final NEOGAUGE metric. And for this example, we argue none of the above 3 solutions are considered to be creative because convergent solutions may lack divergent creativity. You can see like the first state NEOGAUGE at 0, the solution is correct, but the edge creativity is 0. And alternatively, language model can hallucinate responses and resulting in very high edge creativity, but often lack correctness and constraint and the constraint following. You can see the example here is the second one, NEOGAUGE at 1. It is wrong solution but has high divergent creativity. So in our experiment, we trying to answer the following 2 questions. Are larger language models more creative, and do extremely large models of equal size exhibit comparable creativity? We first demonstrate GPT-4 is the most creative language model thus far by the time we conducted our experiments. You can see GPT-4 consistently achieved the highest NEOGAUGE almost at every state. And but others like Cloud 3 and Lava 370B, they have a close NEOGAUGE at 0 score to GPT-4, but their NEOGAUGE score quickly decreases to 0 within the next 2 states. And these results could potentially answer our research question. Larger language models generally are more creative, but extremely large language models is not necessarily exhibiting extremely creative performance. We also try to answer the following question in our paper: who is more creative thus far, machine or human? And we can see a language model demonstrates minimally higher performance in divergent creativity compared to humans at their lowest level, which is human divergent as stated at 0. But humans has significantly greater convergent creativity than language models in earlier stage. So we can reach a tentative conclusion that under problem-solving settings, language model in the above figures barely exhibit human-like creativity. Finally, we investigate the effect of inference time scaling on language model creativity, and we have this takeaway. Inference scaling slightly boosts divergent thinking with rapidly diminishing returns. We compare the performance difference before and after implementing these 4 different reasoning strategies, and we can see convergent thinking is generally improved except sampling, because that's what these strategies initially designed for, to improve correctness, to improve accuracy, right? But only MCTS improves divergent creativity. And it also makes sense because it rolls out numerous passes during the expansion, and the strategies like self-correction, planning, and sampling, which operate on single trial pass, fail to explore divergent solutions. So here's our conclusion of our work. First, we propose protocols for evaluating language model creativity in problem-solving settings. Second, we introduced the denial prompting framework and NEOGAUGE metric to provide a comprehensive creative evaluation that invites both convergent and divergent thinking. Finally, we release our NEOCODER dataset for future works. If you have any questions, don't hesitate to reach out. And also, here's the link for our paper and the code. Thank you.